All right, come back to me. 3, 2, 1. Okay, so at this point, you've maybe got everything kind of going, flowing through your head again, remembering how to look at delta H's and delta S's. What is the symbol for enthalpy? The symbol. Delta H, right? Loud and proud. And if it's if we have delta H, we have two varieties. Delta H is a positive or it's a negative. What does the positive version of delta H mean? The whole process is endothermic, which means that energy is taken into the reaction. Okay, so endo into the reaction. And then delta H of a negative means what? Exothermic, which means the energy is being released. I'm going to actually call that exit, just so we can kind of see the similarity in words. Just mark you. Oh, shit. Okay, thank you. So we're going to say that energy is exiting the reaction. Exo, exit. That's pretty easy to remember. Which of these is more favorable to the universe? Exo, because actually the reaction doesn't want all that pent-up energy. It's releasing it to the universe, which makes the end of reaction, the end of overall, more stable. And then endo is not favorable to the universe. So I was using happy faces and sad faces to help indicate that. Entropy, what's the symbol? Delta S. And there's a positive and a negative variety. Positive delta S and a negative delta S. What does the positive one refer to?
More disorder.
More disorder, good. And naturally that occurs really easily because things don't want to be tightly packed together and really pent up in their potential energy. They prefer to be released as well in a disordered fashion. And so what does negative delta S refer to? Less disorder. So you're remembering that delta S entropy is referencing the disorder, which we know naturally that also helps us understand the order, but it does, like, by definition mean disorder. Which is more favorable to the universe?
More disorder.
More disorder. Okay, so if more disorder and exothermic reactions happen, what would we say about the spontaneity of that reaction? Always spontaneous, without a doubt. It doesn't matter if you have a catalyst or if you have high or low temperatures, whatever is happening, they will always happen. It doesn't mean it's happening fast. It just means it's like legit going to happen. Like what happens to coal over long periods of time under high pressure and high temperature? It turns to diamond, right? Coal turns to diamond under very like extreme conditions. It does not happen overnight, people, right? Because if not, diamonds would be in such surplus. There's no problem with that. You know, they'd be cheap. But it happens over a long period of time, spontaneously, but really slow. So don't think spontaneous means like happens like that. Okay. Okay. So down here, these are reactions that you have had a moment to look over. So I want to talk about just a couple of them. Okay. So if we're looking at the second to last one, this one right here, we have O gas plus O gas. That's like a monatomic ion or a monatomic gaseous atom, another monatomic gaseous atom making diatomic oxygen. Is that balanced?
Yeah.
Yes, right. 1 O, that's 2 O's, and then we have a diatomic. Okay, tell me about the delta H of this one. Positive or negative?
Negative.
It's negative because heat, which is a form of energy, is on the product side, which means it's being exited or released. So that's negative. Is that good or bad?
Good.
Good. Universe is happy so far. It wants that to happen. What's happening to the entropy?
It's
I don't know how far you guys got in that discussion, so let's talk about this. We're looking for disorder, right? There are two ways we can look at disorder. Simply looking at states of matter or number of moles to help us indicate if something's going to less stuff to more stuff or more stuff to less stuff. So states of matter, what's the increasing disorder in states of matter? From what to what to what? Right. Solid, liquid to gas. So if we start with solids and we make gases, heck yeah, the disorder is really increasing. But here we have gas, so we can't really look at states of matter. So instead, our kind of second line of defense is looking at number of moles of everything we have. So how many moles of oxygen do I have here on the reactant side? 2. You just add up coefficients. It's like mole ratios. You're just going to collect them together though. So there's a 1 plus a 1. That gives me 2 moles of gases on the reactant side. How many moles of gas on the product side? Only 4, just one. So we're going from 2 moles of gas 2 crazy moles of gas, right, to 1 crazy mole of gas, what's happening to disorder? It's going down. It's getting more ordered, right? 2 crazy moles, 1 crazy mole. It's getting more ordered. So that is a positive, right? Less disorder, more order. Less disorder is a negative value. Is that good or bad for the universe? Bad. So I'm putting in frowny face. Okay. So is this reaction spontaneous or non-spontaneous? Right now we're saying it's non-spontaneous, but when we're in the video we had like a caveat. We would say spontaneous at, anybody? Certain temperatures, right? Not all temperatures is it going to be spontaneous. So at this point, from this question, I could just say it's non-spontaneous because it's definitely not always spontaneous. Or you could say spontaneous at certain temperatures. All right, give me a 1 out of 10. Do you get this example? This first example. All right, let me do another one. Okay, so I chose that one because I thought that was the hardest one, and if you got the hardest one, you could do any of them. So, give myself some space here. Okay, so let's work from the bottom. Okay, so we have zinc solid reacting with 2 hydrochloric acid aqueous reactants, make zinc chloride, hydrogen gas, and heat. Tell me about the delta H.
Negative.
So we see heat's on the product side again. It means it's being exited or released from the reaction. Negative. Good or bad?
Good.
Yay. Okay, so that's good for the universe. It satisfies the requirements of the universe. Tell me about what you think right now about disorder.
It's going up.
So what's a key sign you see right here, Elizabeth? So we're starting with solid and 2 aqueous compounds, right? And we're making aqueous and gas. I don't know if this is balanced yet. Okay. So regardless, there's aqueous involved on both sides, but we're certainly increasing disorder because we're going from a nice solid, if you guys could turn your phones down, it'd be great, solid to gas, which is very, very increased in disorder. So what's happening to delta S? Is it positive or negative?
Positive.
Positive. And tell me about that. Happy or sad?
Happy.
Yay. So then what do we have here?
Spontaneous.
Spontaneous always, because there's no temperature requirement causing this to differ. Okay, those are the main concepts for that, okay? So we will kind of plug that in some of our discussions with reactions and in our actually next couple of units. So you'll see this stuff again. I wanted you to get the basics so that you can apply it in any situation. Okay? One fun fact we should know, anytime you have a combustion reaction, think about what's happening, think about what you see, think what you feel, and I want you to tell me if that's an always endo or an always exo reaction. Combustion. What's happening with combustion?
We don't carbon.
Okay, so it's maybe if it's a hydrocarbon combusting, if you're releasing carbon dioxide and water, what else do we generally see or feel with combustion? Heat and fire and light. Okay, so if it's releasing all of that energy, what kind of reaction is it? Exothermic, 100%. Like combustion is always exothermic. So we're going to do a combustion reaction. Okay, so let me tell you what's up here. So I still need to make sure I've got enough space. We have our big science night celebration, so that whole back area is a hot mess. But we're going to work up here in these lab stations. The way this will work, pull a piece of paper, because you're going to do 2 activities on this paper, and you're going to turn it into the box when you're done, okay? 2 activities are done on this paper. So call the first one Smorechiometry. Smorechiometry. And go ahead and draw this little table, this pre-lab table, and in your groups right now. Actually, yeah, draw this pre-lab table, and then I'll let you guys do it in the back in a second, okay? A couple of you guys are supposed to get mail, and did not get straight my bag. This is teacher tomorrow. Your transportation form, which literally every person has in this room, turn that to your homeroom teacher tomorrow. All right, so just sketch the table right now. So I'll have you guys write your reaction and your complete the table in the back. All right, so what we're going to do is we're going to start with writing the reaction for the perfect s'mores, and we're going to use like GC for graham cracker, M for marshmallow, C for chocolate. Like, don't try to make it like a legitimate reaction, okay? This is kind of for fun and learning. After you get your reaction, you're going to complete the table based on how many food items you have, how many products, aka s'mores, should be able to theoretically be made utilizing those quantities. After you get that done, at your table groups in the lab, you'll actually go ahead and synthesize your own s'mores using the Bunsen burners. I will have this little assembly line for you guys to come through and get like your ingredients, so just you touch your own stuff. I would prefer if you got a couple paper towels at the table so there's not crumbs literally everywhere, okay? After that, you guys will do some questions, and then as you finish some questions, I'll call you guys back up to get second rounds, and then do some more questions. This should take us about half an hour, so you're going to decompose your s'mores in your stomach, right? So everything's chemistry related. After that, you guys can see on the board that you're working on a combustion stoichiometry carbon footprint activity, which is going to be under the website. So you'll come back to your seats and get a computer, okay? All right, let me scroll back up if you need. Oh, let me actually show you this first. So after you write your reaction, only get enough reactants for one product so that I make sure I have enough for everybody. You must add heat, aka use the Bunsen burner. Don't forget how to light the Bunsen burner. You know, I get a little irritated. I'm sorry. Hormones. And then decompose your product, okay? So I'm going to leave that there for you. You guys can choose a partner right now to work with. Make sure you have shoes and goggles. Go.
Let's get it.
The gas is not on yet, so do not try to turn it on yet. I'm here. You finish your video first, okay?
Wait, you said for the second one, okay?
Okay, yep. Finish your video first.
Where are we going?
So goggles and a person. Set up a Bunsen burner. Hey, Ezra, can you guys push this whole thing up some? So begin setting up your Bunsen burner. Do not let push. There's more than 4 people that can go back. Push. There's no space for your guys. I don't have the gas on yet. Alright, the gas will be on in less than a minute. Is your Bunsen burner set up appropriately first? You can't remember how to do it. You're not like it yet, guys, because I need you down to 1, listen. 2, there are little worksheets at each of your stations. Stop touching the triggers. Okay. There are worksheets at each of your stations. Please make sure each group has that as reference. Go ahead and fill out the table if you've not filled out the answers to that table. And we'll call up groups and grab the materials. If you need to wash your hands and grab some paper towels, now's the time to do it.
Wash your hands and at least minimally grab paper towels. So I'm not putting them y'all next, so you guys can grab a paper towel from the plate. One each second. Alright, once you get the table done, I'm calling you guys up here. Sorry, yeah, I'm right. Right on the layout, so the last in the line. You guys can stand in line now. You're not marshmallows and more than one person can stand at the little station, so scoot your butt down here. There's a line. You guys can begin. Get your butts on the lid if you are ready.
You're out. You're
Three strikes and you're out, people. Make sure the gas is on. I'll listen to it. Make sure the gas is on.
Yeah, that's what I'm going
It's on now, it's on. While you're decomposing that product, you can begin to answer questions. Answer questions while you start Alright, listen for me. 3, 2, 1. You should be in the process of the process of answering some questions. At this point though, your Bunsen are still going because I'll call you back up. You're fine, you're still fine. I'll call you back up after you get through a couple more questions. But I do want to make sure our reaction is correct because later on you're going to say geometry at the bottom. What's the reaction here? What's the ratio? How many marshmallows? 1, right? 1 ill. How many grams? 2 GCs, right? 2 graham crackers. Chocolate. 1. You broke it in 4, right? But we want our ratio to be 1. And then how many s'mores does that make? 1. So it's a 1 to 1 to 2 to 1 ratio. Okay? Let's see where we are. The people who get the farthest will come back jump ship first.
I think it's not referring to that's more.
Well, I mean, light it back up. Well, you can't. I like it. Alright, anyway, it's not like a All right, when you get to question 5, let me know. When you get to question 5.
Incomplete s'mores is my base material. So would it be 15 or I think that's reached 15. Would it be 15? The marshmallows and graham crackers are so with the marshmallows 15.
Which item will you accept?
Perform so that they can only get a certain
You say like a long, like
No, that's once you get through with 5, you can stand in line for another sport.
I got the last big one.
I smell somebody's want to learn it, and you guys make sure.
Honestly, I thought you could go home.
No, go ahead. Let me get some more of those. Keep your graham crackers, and then big swamp.
I think it's definitely honestly. You're not that nervous.
I think I did.
I was close to that. Bro, I'm thinking of my heart, bro. I don't like it, no, this is like. Where were you?
Alright, has everybody got the second s'more?
Me on our second.
Alright, everybody should have gotten their second one, and you should be finishing number 6 very soon. If you need a calculator, grab a calculator. Absolutely. I'm here. Give me a call for your calculator.
Just like.
We don't go on in a second.
Not even why are you gotta get it down together for the next question.
Anybody else?
Mainly because I'm not coming for questions right
I'm watching my hands.
Alright, some of you guys may have already gotten started, but listen up for me, okay? So, at this point, I'm going to say this will take you until about 10, so about 20 minutes. We're going to see. But the idea is that you can apply, can you guys stop for a minute? Thank you. You can apply stoichiometry to real world examples like s'mores, cooking, baking. We've been talking about that one. But do you guys know what carbon footprint means? What's it mean? Let's see, somebody. Say again?
Carbon emissions?
not just carbon. Well, it's carbon, but it's in the form of what? CO2. Thank you. Methane, carbon dioxide. There's a lot of things with carbon in it, but we emit this every day via, not from us, like not respiratory system, but like through energy processing and energy uses. So there's a brief background I want you to read, and then after that, it basically has you start looking and doing some personal reflection on your contribution to the carbon pollutants in the world, nationally and then globally. So basically, you'll look through, you have to read that paragraph first to answer these questions, and you'll look at the EPA's website to get some information about gas emissions. And this is in honor of Earth Day on April 22nd. As you continue to look through this, you'll find that you might reflect and say, hey, I can probably do better. Where can I do better? So I think from here it's all self-explanatory. It is kind of personal, like you can ask each other questions, but when you get to the point where you have to like calculate mileage that you drive from home to school every day, that of course is going to be you. Like Google Maps, that's you. So some of this is partner conversations, some of this is personal. Okay? No, you are writing this on the back of your Smores lab. You're trying to send it to the class. You are writing this on the back of your Smores lab. That's why I said have it together. So that is under my homework website. Under homework, yes, the link is in homework.
Welcome to the mini morning news show, where we are so excited about Chick-fil-A's showing minis for breakfast and eat mini 5 minutes. In fashion, teacup poodles are the latest fashion accessories. In weather, mini umbrellas. Still don't keep you dry. In film, a big blockbuster gets a mini